I've recently looked in much more detail at the projection model inside the Oculus Rift, and it took me a while to really understand what was going on. So I figured I would make a video about it. So what we have here is a simulation program that kind of simulates the way how the Oculus does its projection, and then how the viewer would essentially perceive the three-dimensional objects that get drawn. So on the left side here we have a kind of scale model of the Oculus Rift. We have the viewer's two eyes, the pupils are right here and here, the fovea on the other side of the eye is right there and there. Here we have the lenses that make viewing possible, and then of course here we have the left screen and the right screen split in the middle by that barrier there. Now, in order to talk about what's going on, let's first talk about how basic 3D perception works in the context of an HMD, and for that it's easiest to momentarily ignore the lens, so I'm going to turn that off, and then have a little look-see. So, what do we have here? On the other side of the HMD we have a virtual object, this purple square here, and so now what happens is that the software will project an image of this object onto the left and right screen, and that will be viewed by the viewer's eyes, and let's see in detail how that happens. So let's say we take a single object point here, that vertex here right on the corner, and then to project that point onto the screen, the software draws a line from that point on the object to the programmed in camera position, which is the red dot here, and wherever that line intersects the screen, the left and the right screen, it draws a pixel, that green guy there. So then that pixel emits light, and the light from the left and right screen enters the viewer's left and right eyes through the pupil, and then hits the retina just about right here. So this is then where the viewer's visual cortex kicks in, and it sees that there is light from an object coming in on this position on the left eye and that position on the right eye. So the brain kind of traces back the direction of the incoming light, because it knows it has to come in through the pupil, so it can trace out the intersection of these. It can trace out these two lines. And because light travels in a straight line, our visual cortex knows that the original object must have been at the intersection between these two lines on the left and right eye. And as it so happens, of course, if the projection was done right, then the two lines intersect precisely where the virtual object was positioned, and our brain perceives precisely what the programmer has put in to be perceived. And in order to do that, obviously we need to know the position of the virtual object, we need to know precisely the position of the two screens, and we need to know precisely the positions of the viewer's pupils. Now let's have a look what happens when we don't know those things precisely. Let's just pretend that the viewer's eyes are somewhat farther apart than they were programmed in. Right now the eye separation is set to 64 millimeters, which is sort of the population average, and is also the default in the Oculus Rift. Also happens to be the distance between the two lenses. So let's make the eye separation a bit wider. Let's say we put that to 70 millimeters, and so now we see how things go wrong. We still have now the green object is actually the programmed in virtual object. So as far as the computer is concerned, as far as the rendering engine is concerned, we still trace a line from the point on the object through the programmed in camera position, which is the red dot. The viewer's pupils are now these white dots here, which will intersect the screen in this point and that point, and then the viewer will perceive light from the screen, of course, but now because the viewer's pupils are positioned in a different place, light from the pixel on the screen will enter the eye along this line and then hit the retinas, and so now the brain, not knowing that the camera position was wrong, will trace these lines back out, and of course these purple lines intersect somewhere else, meaning that the brain will actually perceive the original point not to be here but to be here, and if we do that for every point on the object, we'll get this diamond shape, this distorted shape here. So that means that if the viewer position doesn't quite match, then the view will be distorted. In this case, the objects will be squished in the depth direction and a little bit in the lateral. And that's a problem. It's not just that the objects are distorted, but now if they're moving, let's just spin the object, or if the viewer is moving through the virtual environment, what happens is you see that the objects are not just distorted, but they distort differently depending on their orientation. So they get squished and warped in very odd ways as the viewer is viewing them. And real objects are solid, they don't behave like that. So what's happening now is that the viewer's brain essentially says, oh, the world looks like it's made out of jello, the real world is not made out of jello, so that means I probably ingested some toxic substance and have to purge the system, and then that of course leads to severe nausea. So this is why misconfigured viewing parameters are another cause for motion sickness or VR sickness in head-mounted displays. I haven't done the research whether they are bad or better or worse than lag, but it's on the same order of severeness. So what it means is, of course, that in order to combat this, we need to know the viewer's eye separation. So in other words, the program needs to be told that the eyes of the viewer, or the pupils of the viewer rather, are 70 millimeters apart as opposed to 64. If I do that, if I now change the camera position to again coincide with the actual pupil position, then of course everything matches perfectly. And this is not only true for the eye separation, but it is really true for the 3D position of the user's eyes. Now this is a top-down view, so we don't have third-dimensional adjustment, but let's just say that the viewer is a little bit farther away from the screen due to whatever, wearing glasses or having a different facial structure than the programmed-in camera position, and again the same thing happens. So now for that also the camera has to, wrong direction, the camera has to adjust, and then everything is fine again. So far that is not really anything that is new. It is a basic truth that you have to calibrate an HMD for each person to match the position of both pupils precisely in three-dimensional space, otherwise it will not work properly. While we are talking about this, there's another little issue I want to bring up, and that is, if we now look at the eyes here a little bit closer, there's a reason I drew the fovea. The resolution of the retina is not uniform. It's a very high resolution around the fovea, which is the central point of the retina just across from the pupil, and then it gets lower and lower and lower as we go around. So when a viewer sees an object at some distance here, there's an automated response that will mean that the eyes will start swiveling inward until light from the object precisely hits the fovea. That's a foveation response. And so what we'll do is, I have a slider here to do that, so I can do that exactly. I can rotate the eyes inwards, so now that the light from the object hits the fovea, more or less. Which of course is now the problem there, that the eyes, when they swivel, they rotate around the center point, more or less, but not around the pupil. So now, due to the rotation, the position of the pupil has changed, and again, just as before, the virtual image is off. And the only way to correct for that is to somehow know that the viewer has rotated their eyes, and then adjust the camera position again until things are more or less perfect. Here in this case, the reason why it's not completely perfect is simply that the granularity with which I can move the camera position in the software doesn't quite precisely match where the pupils are, but that's a technical detail. So what that means is that the viewer's eye position is not constant throughout the lifetime or the runtime of a program, but it changes depending on what objects the viewer will look at. If the viewer looks at an object that's far away, then the eyes will be more or less parallel, and if the viewer looks at an object that's very close, they might be swiveled all the way in like this here. But of course there is not really a way of knowing what the viewer is looking at, so which is why it would be really neat to have an eye tracker in the HMD that would in real time give us the precise 3D position of the pupils, so we can always in software adjust the camera position to precisely match that and not have any of these issues. As you can see, if you do not do this adjustment, even a small convergence angle of 12 degrees in this case is a pretty severe distortion in the depth perception. The object is now perceived at about, at least, I would say 40% larger distance, and also quite severely distorted. Again, if you animate that, you can see how this is definitely not a good thing. So this is not a minor effect, it's actually a pretty major effect in this case, because the viewer's eyes are so close to the screens, which means that any kind of minuscule mismatch will lead to pretty severe distortions. But let's ignore that. That's just something that is currently not in existence. I don't think there's any head-mounted display I know of that has eye tracking built in, but it really should. When people talk about eye tracking, this is the primary reason why it should be there. So let's set the eyes back to parallel and now talk about the thing that we've ignored so far, and that is of course lenses. Like I said earlier, an HMD like this one could not work, because here the distance from the viewer's eyes to the screens is very short. It's about 5 centimeters in this case. It depends on the focal length of the lenses that are currently not there, so let me just see what it actually is here. It's from here to there. It's about 5 centimeters, okay, close enough. So you couldn't focus on this, meaning that the image would be completely blurry, and that's why there are lenses. So let's put the lenses back in. Let's see, 1.5, and then let's see what the lenses do to the projection and to the perception. Now you can already tell that there's a severe mismatch between the green virtual object and the viewer's perception of it, this purple wobbly object. And that is of course why we have to do lens correction. Right now the simulator does not do lens correction at this moment. So what is the problem here? We need to look at the geometry again. As before, the camera position happens to be precisely the viewer's pupil position, so far so good. And the software, as usual, draws a line between the camera position and the object point. Where the line intersects the screen, it draws a point, but now the light from that pixel on the screen doesn't any longer hit the viewer's eye in a straight line because there's a lens in the middle. What actually happens is that now the light goes in a slightly different direction and gets refracted at the lens here and here. The reason why there's no refraction here is just that due to sheer coincidence the ray is hitting the lens at a radial angle, but here there's refraction. And so what that means is that now the light is entering the eye at a different angle than it should. And then of course it's going straight again, so it's hitting the retinas here. And now the visual cortex, not knowing that there's a lens in front of the eyes, will just take this refracted line, will trace it back out, and where those two refracted lines intersect, it will perceive the object position, which of course doesn't match the real position. So that is why we have to apply a lens correction, and in the Oculus Rift SDK and in my own software that is done via a post-rendering distortion shader. So what we need for that is we need to know the parameters of the lens to apply that, and I have a little button here that calculates the parameters based on the lens. It's another simulation. So let's do that real quick, and so now voila, it matches again. Now let's have a look at what actually happens here on the display. As before, the software draws or projects rather the object onto the screen by drawing a straight line from the object point to the camera point that intersects the screen here, and that's where the pixel is drawn. But then after everything has been drawn, the whole image is fed into the lens distortion shader, which takes that pixel from here and warps it over there, which is then the new pixel position, which is finally shown to the viewer on the screen. And so now light from this pixel position goes into the lens, gets refracted here, and because the lens correction works, it gets bent, refracted into the eye at the precise angle where it should have been in the first place. So now by tracing back out, the brain will perceive precisely the right thing and everything works. So that is what the lens correction does and how it works and why it's absolutely necessary. It is not just to straighten out the lines in the image, 2D lines in the image that otherwise look curved, but more importantly it is to correct depth perception to the way it should be. So now let's have a look again at what happens when we change the position of the viewer's eyes with respect to the lenses. Right now the viewer's eyes are directly on the optical axes of the lenses, which I haven't drawn here, but just take my word for that. So now let's change the eye separation, and let's go from the population average to a somewhat smaller eye separation, which happens to be mine, because that's where I started running into problems. So I'm setting this to 57 millimeters, and obviously, just as before, now the perceived object differs fairly severely from the programmed in one. So now of course the camera position doesn't match the pupil, and we know what the solution to that is. We have to simply set the camera separation also to 57 millimeters, and we do that, and oh crap, doesn't quite work. Doing that actually made it worse. That's the interesting part. We used to be quite bad, and now by dragging it to be the same as the actual eye separation, it's getting even worse. So what is going on here? And the issue of course is that the lens gets in the way, and the lens messes with this very simple model that we had earlier. The eye is now offset to the with respect to the optical axis of the lens to the bottom, so that means in general light going to the eye will not go through the lens straight, but it will go through the lens at an angle, and at an angle the lens induces a shift. Essentially it shifts the entire image slightly away from the eye. So what that means is that the lens correction is not correct anymore. The lens correction parameters that we calculated for the initial position do not apply in this situation. So what we have to do then is to recalculate the lens correction parameters, which we can do right now. And as you can see now, it more or less matches again, but there are some mismatches right here, and it's not exactly perfect over here. Why is that? And this is because if you now start spinning the model, you'll see, if you look at this very closely, the edge of the model is very close to the edge of the field of view here. It goes right to the edge of the screen, and the lens correction formula that I'm using here, which is the same one that is used by the Oculus SDK, doesn't have enough degrees of freedom to account for that, which is why there is some distortion localized to the very edge of the image, where the the viewer probably wouldn't even see it, but still that is a thing. So this recalculating the lens correction parameters, of course, relies on knowing precisely what the lens is. In this particular case, I programmed in the lens, I gave it a certain front radius of curvature, I gave it a back radius, I gave it a certain index of refraction, 1.5, and so then my program could simulate the lens and could calculate the lens correction parameters for an arbitrary position of the camera. So if I move the eyes farther away, let's see like that, and then make the camera match that again, we see bad things are happening, and then we correct for the lens, and it gets okay again with a bit more distortion toward the edges, as one would expect. Now even more of the object is close to the fringes there. But as I said, in order to do this, we need to know a lot about the internal geometry of the head-mounted display. We need to know the precise position of the lens from the screen. We need to know the exact lens parameters, and we know none of those things from the firmware information, from the non-volatile RAM that is in the Oculus Rift, so we can't actually do this. And as it turns out, the Rift official SDK doesn't do this either. So let's see what the SDK does. Let me go back with everything to the default setting. 64 here, 22, 64, camera distance 10, and let's recalculate the lens correction. And then let's toggle on this button down here and see what happens. So now I set the eye separation to 57, and then the camera separation to 57 as well, and as you see, it corrects for it pretty well. Now I'm calling this here the Oculus lens hack, and that's not exactly fair because it works. In that sense, it is not a hack. I'm calling it a hack because it is not properly described in the documentation, and that really threw me for a loop, which is why I wrote this program here in the first place. What we are doing here is the following. If we look at it very closely, what's happening, as I said, when we are looking at a lens not along the optical axis, the lens will also introduce a shift in the image, and that is precisely what the SDK is doing here. You notice there are now 3 green dots. What happens is, at first, the SDK renders as usual, draws the point where a line from the virtual object to the camera position intersects the screen, and then the next thing it does, it adds a constant shift vector to that pixel position to move it over here, and then it applies the previous lens correction formula, which then finally moves the point over here, and then it goes in. So conceptually, this constant shift is part of the lens correction because it is a part of the position and the optical properties of the lens. But the way it is described in the documentation is that this shift is part of the geometry setup. Conceptually what they're doing is, and the way they're describing it, is that they take the left and right screen and they shift it up or down depending on the discrepancy between the eye separation and the lens separation. And that makes no sense. Because now suddenly what the computer thinks it's rendering to the internal model of the HMD doesn't match reality anymore, and normally it always should. And again, that's why it threw me for a loop. What it really is, the way they're describing it, is an optimization. As you recall, the lens correction in the Rift is done via a fragment shader, meaning for each pixel in the image they calculate the lens correction formula, which is a nonlinear radial distortion formula, and that generates a new pixel. So adding this constant shift vector to that equation would just add another addition essentially to the per pixel operation, which would of course make the whole thing take a little bit more time to do. But because this shift is a linear operation, it's a linear transformation, you can express it as part of the projection. You can factor it out of the fragment shader and put it into the vertex shader, so to speak, and that is just because then this shift is going to be for free, is a performance optimization. But conceptually it is not part of projection, and so that's one thing. That's why I call it a hack, because it is explained rather poorly, meaning that it's very misleading trying to understand what is really going on in the projection with the SDK. But apart from that, as I said, it works. If I set the eye separation to 70, or 71 anyway, pull this out, and you can see it is not perfect because it can't be. Just as in recalculating the lens distortion parameters, if you go towards the fringes of the lens, the correction formula simply doesn't have enough degrees of freedom as implemented, so there is some distortion, but otherwise it's doing a pretty good job. Unfortunately, there's one thing where the shift way of doing it does not quite work, and that is when it comes to distance between the viewer's eyes and the screen. And this might just be due to the way I'm simulating the lenses here. I of course do not know the optical properties of the actual lenses in the Rift, and it might be that they are very special and don't have this problem, but I don't actually believe that. Let's say we set the eye distance to farther away. So you see, of course, there's distortion, and then we make up for that in the camera distance, and now doing it the way the SDK does, you can see the distortion gets worse. So this is because pulling the eyes away from the camera does not introduce a shift. We are still on the optical axis, but it really changes the way how the light goes to the camera. So that is where I think this breaks down a little bit, and why there are still distortions if you change the distance from the viewer to the lenses. But again, this might not be as bad, or might not be the case at all in the actual thing, depending on how the lens is set up. So that's something that I do not quite know at this point. But that's basically the story there. That in order to make a proper 3D rendering on an HMD, you clearly need to know precisely where things are, where the eyes are, where the lenses are, where the screens are, where the virtual objects are. You need to also track the user's eyes over time through the program. This is not static information. If we throw convergent into the mix again, you can see how bad it gets. We need to adjust the viewer position and the lens distortion parameters in real time as we go through the program's runtime. And then, of course, lenses make the whole thing a lot more complicated. Without lens, correcting for either viewer position and convergence is fairly straightforward. But with the lens thrown in, we have to know a lot about the geometric setup of the HMD to properly correct for that. Well, that's all I found out. So thanks for watching, and talk to you later.